Good morning, students. So today we will start a new chapter, that is linear programming problem. Okay. So in this chapter, we need to cover the topics, that is definitely what is LPP, what is linear programming problem, and the formulation, mathematical formulation of the linear programming problems, and the solution of it, that is the graphical method, or you can say the corner rule, and some different types of LPP. So the different types and their solutions, and problems from the NCERT exercise. Okay. So what is LPP? Linear programming problem. Now, what do you mean by linear? I hope you all know what is linear equation, linear inequations, because you already solved linear equation and inequations in class 11. So the linear programming is a method to achieve the best outcomes, such as the maximum profit or the lowest cost, in mathematical model whose requirements are represented by the linear relationship. Okay, so the requirements to this mathematical models are given in a linear relationship. So the linear programming is a special case of mathematical programming. This is linear programming, where the requirements are linear and we need to establish a mathematical model, a mathematical formulation from a problem. Okay. So now, what kind of problem we need to solve in this chapter? So for an example, you can take that a furniture dealer deals in only two items, table and a chair. Okay. Now he can invest 50,000 and he has a storage space at most 60 pieces. That means total number of chair and table, the maximum pieces uh, he can store, that is 60 pieces. Okay. So cost of a table is rupees 2500 and cost of a chair is rupees 500. And by selling a table, he can make a profit rupees 250, and by selling a chair, he can make profit of rupees 75. Okay. Now, how many tables and chair he should buy from this available money, that is the 50,000 money, so as to maximize its total profit? Okay, so assuming that he can sell all items which he buys. Okay, that means if he is buying 50 pieces, then he can sell 50 pieces. If he can buy 60 pieces, then he can sell 60 pieces also. Now he can buy 60-piece table also, 60-piece chair also, or 60-piece chair, or 60-piece table, or 30-piece chair, 30-piece table, or 10-piece chair, 50-piece table. So like that, so many combination we can make, right? Now, in which case he can make the maximum profit, we need to find. So let us take that he can buy X number of table and Y number of chairs, right? And the given condition, since X and Y, the number of table and chairs, definitely they are non-negative. And just look at the given condition. So the total cost that he can invest is 50,000. That is the cost of number of X number of table and Y number of chairs. The total cost will be definitely not greater than 50,000. It will be always less than or equal to 50,000. Okay. And the total number of chair and table, that is X plus Y, is always less than or equal to 60, because he has a storage space at most 60 pieces. So he can't buy more than 60 pieces. Clear? So now if we want to write down the mathematical formulation of the given conditions. So from a table, the cost of a table is rupees 2500. The cost of the x table is 2500 into x, and cost of y chairs is 500y, and the total cost is definitely less than equal to his investment, that is 50,000. And if we simplify it, we can find this 5x plus y less than equals to 100. Okay, so this is the first restrictions for the given problem. Now, moving to the second condition, that is the total number of chair and table should be less than equals to 60, not greater than 60, because he has a space of at most 60 pieces he can store. Okay, so this x plus y is less than equals to 60. So we have two inequations as a conditions for this given problem. And what we have to do, we need to maximize his total profit. So let's calculate his total profit. So he can make profit from a one table is rupees 250. So from x table 250x, from one chair he can make profit rupees 75. So he can make profit from this number y chairs. This is 75y. So this is his profit, right? Now we need to maximize this profit. We need to maximize this profit under this given conditions, where x and y are greater than equals to 0. Okay, non-negative, greater than or equal to 0. Okay, so this is called a linear programming problem, and this is its mathematical formulation. Okay, so this kind of problems we need to solve, where we need to maximize the profit, minimize the loss, and so on. So let's go through some definitions. So in the previous case, we are just taking two variables, x and y. And in generally, we can take in variables for the linear programming problem, where we need to maximize or minimize the function z, which is given by c1x1 plus c2x2 up plus dot 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 up to cn xn, where x1, x2, x3 dot 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 up to xn are the variables. Okay, and the restrictions are subjected to a11 x1, a12 x2 plus dot 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 up to a1n xn, and it is less than equal to, greater than equal to, or equal to whatever the condition was given into the problem. According to that, we will choose the sign, and it is less than or equal to or greater than equal to b1. And the second restriction is a21 x1 plus a22 x2 up to a2n xn less than equal to or greater than equal to b2. And similarly, we can take am1 x1 am2 x2 up to amn xn less than equal to or greater than equal to a constant p, where a11 a12 a1n up to am1 am2 amm, these are all constants. Okay, and b1 b2 b up to bm, all are constant, and the variables are x1 x2 xn x3 and so on. Okay, so these restrictions are this, and definitely this non-negative, that is x1 x2 up to xn, all variables are non-negative. So this function z is called the objective function. So this we need to optimize, that is maximize or minimize the function, is called the objective function. Next, the restrictions for this problem, the restrictions for this problem are known as constants. And this is a non-negativity restrictions. Okay, x1, x2 up to xn greater than equals to 0. Now, let's talk about the solution of this linear programming problem. Now, in your syllabus, the graphical solution was there, but some we will talk about the feasible and infeasible solutions. Now, what is feasible solution? So the values, the set of values, the variables, the values of the variables x1, x2 up to xn is called feasible solution. So the values of the variables are called the feasible solution of the given LPP if they satisfy the given conditions, that is subject to those conditions and non-negative restrictions. If they satisfied the restriction, non-negativity restrictions, that is the all variables are greater than 0, greater than equal to 0, and satisfying the given conditions, then we will call the solution is the feasible solution. And if it is not, then we will call this is infeasible solution. So the solution of the LPP is infeasible if it does not satisfy the non-negativity restrictions. Okay. Now, feasible region. What is the feasible region? Now, when we are solving linear inequations, there you can notice that we are finding a region over there, okay, as a solution. So the common region determined by all the restrictions of the LPP is called the feasible solution, and every point in this region, this feasible region, and every point of this region is a feasible solution. Okay. So the area determined by the conditions on the LPP of the LPP is called the feasible region, and the all the points on the region is called the feasible solution. Okay. And one more thing is optimal feasible solution. What is optimal feasible solution? A feasible solution of LPP is said to be optimal if it is also optimize the objective function, that is maximize the function or minimize the function. Okay, any of them solution, any of the solutions, if it maximize the function or minimize the objective function, that means this solution we will call optimal solution. Okay. So these are some solutions: feasible, infeasible, feasible region, and optimal feasible solution. And in the next class, we will talk about the graphical solution of the LPP and some more definitions of on LPP and some theorems also. Okay, till then, practice it. And if any problem or any doubt is there, you're free to ask. Thank you.